Swayam Prabha. Digital India. Educated India.
Welcome to the course Introduction to Uncertainty Analysis and Experimentation. In this module, we look at data analysis and we begin with an introduction to regression analysis. In general, data analysis encompasses many techniques and methods like regression, then correlations, tests of hypothesis, analysis of variance, and many more topics here. All these largely rely on knowledge required of statistics, and these days we have even seen these develop as different branches by themselves, which is data analytics, big data, and called data science. So, they use a variety of techniques to arrive at to make sense out of data. In this course, we will limit ourselves to the first two only. These require more in-depth knowledge of statistics and can be taken up in a later course, but for many of the basic things one does in science and engineering, these two we encounter quite frequently. So, we begin with regression and start with the definition of regression. And here we have written a basic definition of what regression is, and it says the regression determines the strength and nature of the relationship between one independent variable denoted by y and one or more, which is a set of other variables which are the x's, which are the independent variables. So, it says that we make a relation, a mathematical relation or a formula, or you can call it a function, usually a continuous function, where y, which is the dependent variable, is a function of various independent variables denoted here as x1, x2 and x3. So, this function can take many forms, but as long as we have a function like this, what we are saying is that when we generate this type of a function from data, in this case it could be a combination of data from experiment and or other sources also, then we make a function with these things and we generate some constants, and that becomes our complete regression function. So, that is what we are meaning by first making a relationship between these variables, and then so that this is the nature of the relationship, that what mathematical shape it takes. And then we also have to talk about the strength of this relationship, that how strongly are these two sets connected to one another, which is to say how strong is y connected to x1, x2, x3 and so on. So, this is what the idea of regression is, and what we are looking for in this set of lectures is that I have data from my experiment or from others' experiments or some other published data, and I want to generate an expression y as a function of these variables. So, this is our objective. Now, a word about where these variables are from. In general, the dependent and independent variables could be from one or more sources, and here are the various possibilities. All of them could be from our own experiments, and within this we could have done just one experiment, which we have so far called single experiment. And we saw in the uncertainty analysis of a result what were the techniques we used for a single experiment. We also saw a technique where we said there are multiple experiments, repeated experiments. So, our own experiment could have also generated data from this. So, that is also okay. Now, there could be situations where we have maybe some of our own experiments and some data from others' experiments. So, if others have done an experiment with the same independent variables and the same values. For instance, so we have say y as a function of x1 and x2, and we collected data at x11, x12 and x13 and x21, x22 and x23. So, these are the independent values that these variables were taken used in the experiment. Then if the other experiment done with a similar setup or maybe slightly different setup also repeated the experiment at these very data, then we can also use that data for generating a regression. Or it could be a case that we took data at certain values of these, but somebody else using the same apparatus, or maybe we ourselves using the same apparatus took data at some other values of the independent variable. So, instead of this we took it at say x1, 5, x1, 6, x1, 7 and so on, and this at x2, 4, x2, 5, x2, 6, where these are different from any of these. Or it could be that they are all different, or they could be that some of them are the same. So, you could have this data set and x11 and here, which are completely different from here, or you could have a set x23 and the rest of these. Any of these combinations are possible. Their implications on regression are different. So, that is what we have written here, that the available data could be at the same values of the independent variable as we have seen just now here, or at different values of the independent variables, which is what we saw in this second set over here. So, all these possibilities are there, and in general we can use the regression for this, and in the current course we will limit ourselves to either of these, this or this, and we will say that I have generated all the data either from a single experiment, or I have generated data from multiple experiments, and now I want to develop a regression. These require advanced techniques in analysis, and so they are left for an advanced course. So, now let us connect that we have done regression, we are doing regression now, and we have already done uncertainty analysis. What is the connection between these two? So, from an experiment we have seen that this is the basic nature of our formula. We said that R is expressed as a function of x1, x2, xi, so on, xp, and some constants and independent numbers. Now, what we meant x1, x2 and all these xp were independent parameters. Which we would also say were independent measurands. So, there were different parameters that were measured during the experiment using some set of instruments. So, we got all the data. Our data from the experiment is for variable 1, x11, x12 and so on. For x2 variable, we got data at x21, x22 and so on, and like that for every measurand. this was our complete raw data set that came out of the experiment, and then we put it in a result relation. We looked at the analysis for a general case where there is a result relation called R, and we did not put any restrictions on what shape it took or why it was there. Now, when you look at this, we say that in an experiment, after all this data was collected, I could do a calculation for one result, we will call this R1, based on a certain combination of these parameters. Then I will use some of the other parameters and I will calculate another result which I will call R2. And like that, we could calculate many other result relations. So, the point is that from the same set of data that we got from the experiment, we could generate different results. And an example was there that if we make measurements on a wind tunnel on a body experiencing aerodynamic drag, we got one result as the drag coefficient, which we defined as F upon half rho v square into area. And the other variable we could make was RED, which was rho v d upon mu. In the experiment, we measured velocity, we measured area, which also the diameter, and we got this, and we measured the force. From the same data set, we took rho v and d and got drag coefficient. We took only v and d and got Reynolds number. So, we could think of drag coefficient as result formula number 1 and RED as result formula number 2. The issue that comes up here and why we are not going to be looking at these type of situations is that when we do the uncertainty analysis, uncertainty in V is coming here, uncertainty in V is coming here. So, the same uncertainty is coming in this and also in this result. That means that the uncertainties in these two parameters are correlated. And in this course, we are not looking at correlated uncertainties. So, now we come back and say, well, what am I going to plot, make a regression of something against something? And so, I need to define what is the independent variable, and what is the dependent variable. And we have many possibilities over here, and we will go through some of these. The first possibility listed here is that all the independent variables are our measured parameters, xi's. And we pick up this thing and make a plot against one of these. So, an example could be that we measure displacement of a spring. So, the weights that we put on the spring would be our independent variable xi, and the dependent variable that we got was the deflection that we got. So, that is a one on one. So, like this we could have more combinations. Or we could have all our measurands xi and y, which is our dependent variable, could be any of the results that we have generated. So, this is what is called as Rj. It could be any of these results that we have, which we have just seen here and called them as R1, R2, R3 and so on. That means, we are making a regression, in this case between one measured parameter and another measured parameter, or in this case against a measured parameter and a result from the same experiment. A third possibility is that we could make a regression between any of the result relations and another result relation. So, we have R1, R2, R3 like that. So, in this case we could make a regression between R1 and R3. So, that would be a mathematical function that we are looking for. And yet one more thing I put here is that we would make a regression between any of our result and any of our measured parameters. So, any of these are okay and possible, and we often do various things like this in the type of work that we come across. And we have excluded in particular data from others' experiments. So, we are all saying that all these things we are doing from our own experiment. Later on we will see how we can modify this and say compare same independent variable between our experiment and somebody else's experiment, but results from our experiment and results from the other experiment. So, next is how do we get the various uncertainties on this. Next we see what are the objectives of regression. So, why do we want to generate a regression relation? And here there can be many options or possibilities and reasons for doing this, and I have listed some of them here, we can add more. First, we want to develop a regression for our data and use it in our own interpretation. The regression tells us what is the functional relationship between one variable and another variable, and that gives us maybe insight into the type of experiment we are doing and the type of result we are looking for. So, that is one possible reason for doing it. The second reason is the constants that come out of a regression analysis, they are of use to us. For example, if it was a spring deflection and weights that were put here and deflection of a spring, then you would get some points like this, and we are interested in the slope. That is what we call the spring constant. So, that is an example of where we say that the regression constant is of use to us. A third reason could be that we make a regression, we call it a curve fit. So, between data points that we have, we made a curve, and they said that then we say I will use this in my experiment for future predictions. So, the example of this is that we could calibrate a thermocouple and then say that in my experiment I will measure the EMF and use that curve fit to calculate the temperature. So, that is what we call curve fit. Then we could like to do something on scaling and extrapolation. If a parameter has got dimensions, we generally cannot scale it, but if we make a non-dimensional number out of it, like so many non-dimensional numbers we come out in various engineering disciplines, say like Reynolds number, then we know that if we did an experiment with air at a particular Reynolds number, then what we saw there is likely to be the same case with water at the same Reynolds number. So, that helps us in scaling, and even also that if we took a correlation for a range, maybe we would be able to predict something bigger than that. That would be extrapolation. And yet one more objective could be that we generate a regression from our experiment and we want to see how good does it compare with some regression that is already available, and maybe we can even prove that we have done a much better experiment and the existing relation which is already there has been improved, and we propose a better regression. We see these things happening all the time in various disciplines, and every time a better regression comes, we have a slight improvement in whatever object the engineering we were doing. And like that you can add many more reasons why we would like to do a regression. In this course, we will look at this and this as our primary objectives, and we will also see why curve fit comes in. We will not go too much into the detail of scaling, for which you would like to do non-dimensional analysis or use similitude theory, that we will not do in this course. The last one requires comparing one regression with another regression. It requires more advanced techniques that we will not go into at this point. Now, before we go into the mathematics of it, we need to do something about our bookkeeping. What is happening now is that we will use a bunch of symbols, many of which we have already used in our earlier analysis. So, there could be a good deal of confusion that we could generate by saying what does this symbol mean, and say in the case of regression analysis this is what it means, but in uncertainty analysis it meant something else, or it could be a symbol that we use in regression, whereas in statistics we have already used that symbol for something else. So, we will spend some time to do this clarity on bookkeeping and be clear that in this analysis, which is the regression analysis, a symbol that we use here, it has either the same meaning or a slightly different meaning, if so, what it is. So, here we are. From the experiment, we got symbols xi and rj. Although we did not use rj that much, we have now introduced it, saying that result was r, and if we generated multiple results from the same experiment, we just called it r1, r2 like that, and we have called this rj. And we have two variables there in the regression, the independent variable x and the dependent variable y. And the main thing about what we will study here is that we will look at the simplest possible case where we have only one independent variable. So, there will be many instances where there could be two or more independent variables. Those we are leaving for a later discussion, not now. So, with one independent variable, we only have y as a function of x. That means, everything else that is there in this function, they are constants. So, if we want to look at our result formula, if we were looking at the result formula could have more than one functions, the way we have looked at it earlier, but now we pick up one here and one here. And as we have seen in the earlier slide, what is it that x could be x and what is it that we could consider as y, and here is what we are seeing, that x could take any of the values of xi, but what we are saying it, x is one of the independent variables xi or a dependent variable of the experiment, which is like we set some value, say the heater power, and measured the temperature. So, in that context the temperature became a dependent variable, but now once we have got the data, that temperature is also part of the xi, and this is what it could be here. So, what we are looking at is that what we considered as independent variable for regression is slightly different from what we talked of as independent variable in an experiment. In the experiment we said that I have x1, x2 as my independent variables, which meant that while doing the experiment I could set the value of these independently, and then the experiment will do what it has to do, and I have some more measurements that I take, x3 and x4 parameters. They are indicated to me by the experiment, and those are dependent parameters of the experiment. However, all the data that we got from the experiment was all of this, and using some combinations of this we calculated our results R1, R2 and so on. In the context of regression, any of these could be our independent variable, and that is what is written here. We are saying now that any of xi's which were here or any of the results that we have computed which is here, this could be our x. X is our independent variable. Now, we are talking of regression. and this we will denote that it takes some values which we denote as x subscript I. So, x I now has a very different meaning. It is the value of the independent variable that we have chosen. It does not mean that these are the values of the variable x I, or say if this is x 1 does not mean that it is a value of variable x 1, which was this variable here. This means that I am taking a value and assigning a value to either of these x i's or to any of the r j's which I have selected. So, this could be say r 2, and the first value of r 2 that we use, that will be small x 1 for our analysis. The second one would be x 2 and so on, and that is where we get x I, and it goes on there. So, x I is denoting one value of the independent parameter, whatever it may be. So, this is our independent variable x I. Now, for the dependent variable, that is y, and a few minutes back we saw that y could be any of these, y could be any of the parameters of the experiment, independent parameters or the dependent parameters, or it could be any of the results that we calculated from the experiment. So, that is what it is said here, that any of the x i's or any of the r j's, we will call that whatever we take, we call that as y, and y takes the values of y I. That means, whatever we took there, whatever values we had for those cases, they are y 1, y 2 like that. Further, with the restriction that this y corresponds to the same value of x, x I. So, our first number could be a result r 1, and we pick up and we want to make a regression with x 2, then the first value of r 1, which will be x small x 1, must correspond to that same data set from which this calculation was done. So, it will be x first value of x 2. So, that is what it is, x 2 and r 1 is what we want to make a regression. The first value of r 1, this is y, say this is x. The first value of this, we will call it y 1, and it must correspond to the first value of x 2, which we call x 1. So, this is an important distinction we are making of what we mean by independent variable in regression, what we mean by the parameters and the result as being a set from which we pick out an independent variable and a dependent variable. So, if there was only one independent variable, we generate a data set x I, y I depends how many readings we have taken. If there are two variables in the experiment and we want to make a regression on that, it could be a variable x 1, x 2, which x 1 could be either of these which are listed here, x 2 could be any other one from this, and y I could be yet another one from this set. They all must correspond to the same experiment. So, that is an important part. And the same thing could happen if there are more than two independent variables. So, what we are saying is, we are not going to be looking at this in this course. We will restrict ourselves to this one variable regression. Now, we get one more data that we have already done in the experiment and looked at in our uncertainty analysis, input that we will require for doing the regression, and that is that with each one of these we have an associated standard uncertainty u x 1 bar, and similarly for each result you have standard uncertainty say u r 2 bar. All these values we are carrying forward from our previous analysis of uncertainty. And we will see how these become useful in our analysis. So, data that came out of this, that is one, and its uncertainty that there, that is the second one. This is our input data for performing a regression. Now, let us look at what is the nature of regressions that we can have. For a moment, let us not just look at the linear regression, but look at the type of functions we can get in general. So, the idea of, we will first of course restrict ourselves to a linear regression, and linear means that y is some constant plus C2 times x plus C3 times x square plus C4 times x cube plus so on. This is a linear regression. And linear regression of 1 on 1, one independent variable, one independent variable. To give an example of a nonlinear, we could have y is equal to C1 plus C2 x1 y1. So, that is what we are getting there. So, this is for two variables. Then there could be other possibilities. We could have that y is equal to C1 times x to the power C2. Now, this is not a linear relation, it is also exponent here, or it could be ln also, that y is equal to C1 ln x. Or we could have y is equal to C1 e to the power minus C2 by x. This is also nonlinear. Or it could be a sinusoidal function, sin C2 plus C3x. Or even y is equal to C1 plus C2 upon C3 plus x. Now, quite clearly, we have only restricted ourselves to looking at one independent variable, but we got many functions which are we will encounter quite frequently, which are not linear. So, what one does is to transform these into linear form, and an example of that could be that, say y is equal to, we take this case, then we can take ln y is equal to ln C1 plus minus C2 times x. So, what has happened now is that we got a relation between ln y, which we will call as our different y, transformed y, as a function of something plus x. So, the relation between these x and y, this is now linear, and in this we can now apply all the theory that we are going to learn. So, in many situations one can do a transformation and bring a nonlinear form to a linear form. So, that is a transformed variable and we get this thing. So, this is one restriction that we will put in the analysis that we do, that we look at only linear regressions. And then one more thing, linear regression would in general mean the expression that we wrote here, and this is linear in one variable. So, we put the second restriction now, it is a linear regression, one independent variable, and a third restriction that we will now put is that we will only look at a first order linear regression. That means only this term is there, these x square x cube terms are not there. So, we look at first order regressions. So, this course we restrict ourselves to regressions of this type. There are many other forms which are beyond these. There are techniques to do that, but we will not be discussing those in this course. They are topics for an advanced course. So, let us see this. First, what is the idea of having what we call paired data? And what we plot here is x, values of x here and y. And what we have is, from the same experiment, we picked out these data and we plotted them here. So, for x, say we got value x1 here and we got this data point here, we got this y1. So, we got these two numbers x1 and y1 from the experiment, the mean values, and we have just plotted it on this chart. Then we take another pair x2 and say this is y2, and we see where they fall, and we say that this is my point corresponding to x2 y2. Like that we can put many more points. And they could lie whichever way they lie, the experiment is telling us this is what it is. So, we got say that many points, and this is our pairs of data that we work with, and so for this we have this many number of data pairs which we call as x1 y1, x2 y2 and so on, xi yi. I goes from 1 to n. That is what is called paired data, pairs of data. And now we say that my objective is, in a linear regression, what you may have already come across is that I want to fit a line to this. So, this is data which we call our sample, and this curve that we make here, this is what we call is a sample regression, or this is also referred to as curve fit. So, this is the first thing that happens, and the curve fit takes the form y is equal to a x plus b. You may have come across this from your school days. A and b is what we call as the regression constants. So, if we did the experiment once, we got these data pairs, we picked up these pairs. So what we have just argued that this could have been any of the xi or any of the rj's, and this could be any other xi or any other rj. And using these pairs, we did our analysis. And this is sample because we got a limited set of data that came from the experiment. So, this is our idea of what are data pairs and how using one set of paired data, we get a sample regression or a curve fit. The method we have not looked at, but it will generate one sample regression or one curve fit for one sample of the form y is equal to a x plus b. A and b are the regression constants. Now, we look at variability in y. So, what we are saying is that from our data, we knew that every one of those xi's and rj's, we learnt how in each of these measurands we could estimate the standard error in that xi, and how using a result relation we could get the standard uncertainty in the result. Now, what is the implication of this on what we are going to see? So, if we go back to this curve, what we are now saying is that this data point that I had, let us take this one, there was uncertainty in this value. So, there was uncertainty in the x value corresponding to this. So, whatever this would have been, say xi, which means that this value would have lied at 95% confidence level between this and this. We are plotting here the mean value that we got from the experiment. In some sense, this is xi bar at of the first one value of this, which we said was comma 1. So, what we denote here on this picture is that this value could have lied in this band, and that is the way we will show this. And this is called the uncertainty band. And at 95% confidence levels, it tells you where the data lies. Same is true with y. This will also have an uncertainty, and this we will denote as like that. So, this is the uncertainty band for y. So, this is for x, this is uncertainty band for y. And that is what came from our earlier analysis. So, what it tells us is that we can expect the point in this two variable domain to lie somewhere in this, or maybe in a rectangle like that, something like that. So, the question then is, how good is this line that we have made, knowing that there is variability of x and y in every point. How do we handle this? So, what we do in our analysis is that we invoke the fact that the independent variable which we have called x, which could be any of these xi's or rj's, this has got some uncertainty u, but this is very much less than the uncertainty of the other dependent variable, which is r j. So, we are saying that uncertainty in independent variable is much less than that in the dependent variable. Practically, we will get a finite value, but it could be that in one case the uncertainty is like 10 to the power minus 3 of that order, whereas this is of the order of 1. Then we say that yes, the uncertainty in my independent variable is very much less than uncertainty in the result. And what it means is that in the limiting case, we could even say that there is no uncertainty or no error in the independent variable x. So, this is one assumption we make, one more, that uncertainty in x is negligible and in any case practically very much less than uncertainty in the dependent variable. So, that is how we would pick it, and in many cases when we looked at the experiment design, in the context of the experiment, when we looked at independent and dependent variables, so in the experiment we picked up the values of the independent variables in such a way that their uncertainty is minimized. So, in general that would be a strategy for designing the experiment, and say that my independent variable, I want to keep my uncertainty as small as possible in comparison to the other parameters. But in regression we could have said that any of those xi's or rj's that we pick as the independent variable, we say its uncertainty is very small. That is one. What that leaves us with that is that in the dependent variable, there is finite uncertainty, variability which we cannot ignore, and we have to factor that into our regression analysis. So, here is what it means. So, here we have x and we will make a plot where we will plot y on this axis. So, you look at it as a 3-dimensional plot, and on this side is the probability of y. And what we do? We pick out one value of x, say here xi, and ask that I do the experiment many times and I get the values of y in each case. And now I plot that. The mean value of y lies over there. So, in this plane, xy plane, this is our data point. But y, while x would have been the same value in every experiment, from experiment to experiment, y value would come different. So, sometimes it will be here, sometimes there, sometimes there, maybe there, maybe there. So, what we are saying is y takes up different values. And there is a certain probability distribution to those values. That means some values are coming up more frequently, some are coming less frequently, and like that. And if we have large enough number of values of y, we can do a curve fit, and for this analysis we will say that this follows a normal distribution. So, y values, all of yi's, yi1, yi2, yi3, I means corresponding to value of xi, all these values, they follow a normal distribution. So, this is what we are getting. And the same thing if you have to look at any other value of x, say we could have taken this value here and we could have got say this value of y. So, this is the mean value of yi was here, this is say yi plus 1 or whatever, and then the same thing would happen that the values of y would be varying and would take the shape of a normal distribution over there. So, some cases the y value would be here, some cases the y value will be there, and there is a probability distribution because of which this function is coming like this. So, this is what is happening, that we have said that we will consider the case where variability in x is 0. So, we have fixed this point and we get one line here, otherwise this also would have been a big line and a Gaussian distribution around that, and then this one. So, we have made some more assumptions now, that variability in the independent variable is very small compared to dependent variable, and we will be considering it as 0, and that the variance in y, this is what we got, which we will denote as sy. We also assume that the distribution of y values follow a normal distribution. So, two more assumptions have come into the analysis. Now, let us see what happens because of this. And again, as before, we will plot x there and y over here, and we will now look at the case where we had one experiment and one set of paired data, second experiment another set of paired data, but at the same values of the independent variable. So, let us try to plot these things. So, first the data points we got is say here, here, there and there, and say we can put one more there. So, this symbol, this is data set number 1, which gives us x1 y1 pairs, which for each point will actually end up being x1 comma 1 y1 comma 1. So, that is this point, x1 comma 2 y1 comma 2 would be this point, and like that. Then we say I did a experiment a second time, or somebody else did the experiment a second time, and we will plot their values. So, this value came over there, over there, over there, here and say here. The point is that we are saying that all these have been made at the same value of x. So, x value did not change. This was x1, this was x2, this was x3, this is x4, this is x5. And the first data point that we just saw, that would then be x1, y1, 1. The second point, this would be x1, y1, comma 2. y2, comma 1. This is from the second experiment. So, this second data point set that we have, which we have put here, 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 here and here, this is our second data set x 2 y 2. We can call this capital so that there is no confusion. So, this is x 1 y 1 and the second one is the second set x 2 y 2. Now, get a third set. We do the experiment yet once again and say now I have got a third set and my data points are like this. So, this is my first data point, the second at the same values of the independent variable, third, fourth and fifth. So, this becomes x 3 y 3. Now, what happens? We take the first person says, I got my data over here and I will make my regression. And so, with these points, some regression was developed and this is the regression number 1, which is this one. The second person says, these are my data set, I will use only my data set and I will make a regression out of it. And so, this person makes a regression and his regression comes say something like that. Third person says, this was my data set, I will make my own regression and so this person makes a regression which goes like this. This is regression number 3. And so, as many sets of such data are there, that many regressions are coming out. Now, the question is, what should we take as a representative regression for this data set? At the outset, we will not discard anybody's data as being bad or as we do not like the data, anything like that. We say that all the data are equally good. So, all the regressions are equally justifiable. So, this is what happens and what we have to do then is that I can do two things with this. What I will do is, for each x 1 I got different values of y, I will take the average of that value y 1 bar and plot it somewhere and say the number comes over there. I will do the same thing for the second one, I will get y 2 bar and plot it over there. Then calculate the mean of these three and plot it over there. The mean of these three we plot it over there and so like that. This is mean of all y 5. I said now I have one set of consistent data, I will make a regression between which I will call x and the y bars. In some situations one could do this provided there is not too much variability at this in any of these points, but still a word of caution in actually doing this type of a regression. Strictly not recommended. So, the second thing to do is that we say that I have all these regressions and what I will do is I will write the equation for each one of them separately. So, here is what happens. The first person gets y is equal to a 1 x plus b 1. So, their regression constants are a and b. the second person gets y is equal to a2x plus b2. The third person gets y equal to a3x plus b3, and as many such regressions were there. What this now tells us is that all these a1, a2, a3, they are like numbers coming from a statistic, they are not the same. So, this forms a new variable, and b1, b2, b3 similarly come from another distribution, and we presume that both these have a normal distribution. This will be the case if all the y's had normal distribution with similar parameters. So, what we said that in the earlier thing, that each one of these are same, in addition to saying that they have a normal distribution, we can also add here that their standard deviation is same at every x. So, this is yet another condition we are putting. These two will come from normal distributions, and so they would have their own population, and from there we could get something else. So, let us see what happens in that. So, we have all these regression constants coming in, and we have if we had a population, that means infinite number of experiments from which the y values came, then we can make a population regression of the nature that y is equal to alpha x plus beta tilde. So, this is the population regression. And the symbols that I have used, they are constants alpha and beta, but I put this tilde on top of that for a particular reason, that the symbol alpha is used in statistics for the level of significance. So, this will lead to a lot of confusion if you were to look at it in that way, and to distinguish it from the level of significance, we have made it alpha tilde and beta tilde. So, our experiments, whatever A's we get, A1, B1, they are estimators of alpha tilde and beta tilde, and we have to give an interval estimate. This is essential now. So, this is one important thing that we have come up with, and this means that we have to calculate u in A bar and u in B bar. And finally, we will define one more term and then we will stop, which is error and the residual. So, we are plotting here y, this side is x, and from the discussion that we just had, we can now make two lines. One is this one, which we will call the sample regression. Which we will denote as y hat as the sample regression predict value. This is a x, a plus b x, and then we draw a second line which is the population regression, which we will call as y tilde is equal to alpha tilde plus beta tilde times x. And if we take any value of x, say here, then we get 2 points, one from the population regression, and this is what we call the corresponding y tilde, and this we call it as y hat. But our data point could have been somewhere there. So, this is the value from the sample regression, this is the value from the population regression, and this is our data point. So, now we define an important parameter, that this difference is called the error EI, and this we call as the residual. So, this is an important parameter that we will see later on, why it gives us a lot of information about what type of regression we made. And we define one more, the difference between this and the population regression value, this we denote as epsilon I. And EI is an estimator of epsilon I, and they both follow a statistical distribution, and that gives us a lot of valuable information in what we want to do. So, what we have seen here, this expression. So, in developing the regression constants, so with that we come to the end of this lecture. We have seen what are the various methods of data analysis, what is regression and its nature, how we can convert a non-linear case into a linear regression, and we will focus on linear regressions, first order regressions, and in one variable. And finally, we said how we will treat variability in the regression analysis by saying that the independent variable has little or no uncertainty, the dependent variable has uncertainty, and we will use this information to further develop our ideas and how to calculate the regression constants, how to calculate a future predicted value, how to calculate a future predicted mean. So, all that will come in the next lecture, that is the evaluation procedure. On that note, we conclude this introductory lecture on regression. Thank you.